So for my project, I worked with Catherine Lent on a numerical approximation of a computer chip using time-dependent 2D differential equations. So starting off with a little background information, a physical phenomenon known as resistive heat or Joule heating is present in anything that we try and put electricity through. Anytime you put electricity through a material that has a non-zero resistance, so not a superconductor, some of that energy that's in there will be lost as heat. The amount of heat generated is dependent on the amount of current that you're trying to put through that specific material and the resistance of that material itself. So the reason this is relevant is because for the last 50 or so years that we have been making massive improvements with the power and capability of all the different computing devices that we use, is because we have been able to put more and more transistors in a smaller and smaller space. So transistors, you can think of them as the brain cells of this chip. On their own, they just send a few signals. They're not really doing much, but when you put them together in a specific configuration, then they can do a lot. So in 1965, Gordon Moore coined Moore's law, which was the prediction that every year the amount of transistors on a computer chip would double. In 1975, he revised that to saying every 2 years it would double. In actuality, it has stayed almost exactly in the middle, with around every 18 months doubling the amount of transistors. Now, this is all great, but whenever you put more and more things that generate heat in a smaller and smaller space, the amount of heat that gets dissipated by that environment decreases, which means that the temperature is going to rise faster and be harder to cool. Now, we have billions of transistors in our computer chips now, but had nowhere near that in the older computers that were much larger. So why are they still working? Why haven't they melted? Well, we have made a lot of improvements in the amount of electricity that is required to make these transistors work. But the fact is, Moore's law is not going to last forever. Innovation and improvements are getting harder and harder to find. Our industrial techniques have, at this point, been very close, if not on par with the research improvements that we've discovered. So it's gotten to the point where we can't just stick more transistors in a smaller space by improving our manufacturing methods. And another issue is that, yeah, we want to have things closer and closer together because anytime electricity travels from one place to another, that signal takes a certain amount of time to get there. And whenever you're doing billions of operations each second, that's going to take a lot more time. That wastes a lot of it. So we want to put things closer together to save time and make our computers run faster, but we can't put them too close together because if we do, the temperature will get too hot and things will melt. Neither of those are things that we can do both of. And that's where computer architecture comes in. So computer architecture does a lot of things, including devising new ways to do things like parallel computing. But the goal of computer architecture is to maximize the performance of your computer chip if you have a given number of components and transistors. So our goal was to model how temperature changed across a chip over time, which means that we need to be able to generate an equation or a function for what the temperature is based on how that temperature is changing at each point. And this is called a differential equation. So we had an equation based on the amount of code or the amount of operations that would have been required at each point on this computer chip. Based on that equation, we can figure out how much heat is generated by that point. And we also have something called Newton's law of cooling, which basically just describes the fact that heat will flow from a hotter place to a colder place based in an amount that is based on the difference between those two temperatures. So with this in mind, we could build a differential equation. But you run into an issue. Most differential equations can't be solved analytically. The nice ones can, but this is real life, so we're not interested in the nice ones. We want the ones that are messy. And that means that we need a numerical approximation. We can't solve this perfectly. But we can solve it pretty well. And one of the way that we chose was the finite element method. This is a way of approximating a really complicated, hard to deal with function by making little approximations of that function around each of these nodes. This is actually what you see on the right. Every point on that upper graph is represented by the average of the values of the nodes around that point. So for instance, this triangle spiking spikes to the approximate value of the point at that node. And in addition to this, we need to add in time dependence because we're not interested in just seeing the temperature of it at time 0 or time 20. We want to know how it changes. We want to know how it changes as heat spreads across the chip. So we needed to add in time dependence to this. I'm not going to go into the details of how all of that was solved, but we were able to get this solved, and we were able to model a specific architecture. So what we chose to model was the Cascade Lake architecture, which is a relatively modern architecture that is used by Intel. So each of these different little shaded shapes that you can see is a different component that is fitting in a chip. With modern processors, we have a number of cores. In this case, this specific architectural chip has 12. So each of these little cores has a bunch of different components in it. What this means is that we had to develop a function that shows how every component in every chip generates heat based on all of the stuff that goes into it, all of the operations, all of the electricity, all of that. So what we did was we approximated this mess using a numerical function using that finite element method. And with these node values, with these values for each component at each point on the chip, we can substitute that into a matrix, which allows us to use linear algebra methods. Well, all of this is great, but how do we decide how much heat is generated by each different point on this chip? I mean, these are shapes, these are components. How do we tie that back to the code it's running? Well, that's where a bit of the physics and the computer science knowledge comes in. So essentially, all of these transistors on their own are the same. So they're all made of the same material. So they all have the same resistance. Every instruction that you send is also going to have the same current. So which means each transistor, if sent with the same number of instructions, would generate the same amount of heat. Well, we're not sending the same amount of instructions to each spot. We're sending some instructions to some cores or some components more often than others. Some components are used far more frequently than others as well. So we related the amount of instructions that were going to be flowing through the average program to these different components on each core in order to decide how much heating was done by each component. And this was what we came up with. So as you can see, as time goes on, each of these different spots begins to heat up. You can also tell that mostly around the cores is where this heat is generated. You don't see much heat actually being generated near the memory controller or the different DDR4s, and that's because those are storage of memory mainly. And memory in a good program is accessed as little as possible because it takes the most time to get an electrical signal to it and then look through it to find your information and all that kind of stuff. So we combined all the pieces of our different architecture, all the different components, and we put all of that together and got this heat map. But the goal of this project wasn't just to make a pretty picture, it was to be able to demonstrate how your different computer architectural choices will affect the amount of heat that's generated at each component, and the amount of heat that spreads across that system. But what actually matters to most of the computer science people, and not the electrical engineers, is how to write code that better suits your specific architecture. So this is with a modified instruction set, and you can see that even with the exact same architecture, by focusing in heavier on certain types of code or certain instruction sets, you can generate less as a whole and also more focused at different places. Now, this is not always going to be possible. This instruction set is very likely to do nothing. It would be very useless to just go back and forth between memory without doing any calculations. But what you do have is specific architectures that are designed for specific types of instructions. The most common example is a GPU, or graphics processing unit. So graphics processing unit, rather than a CPU, isn't designed for general use. It isn't designed to be able to do whatever you ask of it. It's designed to be really good at doing a lot of parallel processes. So it's great for working in AI, and it's great for modeling images, but it's not great at anything else. And this is where the coding goes in. If you're always working on a general purpose computer, then, you can try and optimize your code, but the goal here is not to build a chip that is perfect for one specific type of program that you want to run on it. At least that's not most of our goals. Our goal is to learn how to better write code that uses what our computer chips are good at and stays away from what they're bad at. So the original goals of this project were a lot more than what I ended up being able to do. So we wanted to have a number of different architectures that we had represented. We wanted to have different chips. We wanted to make sure that we wanted to be able to move around these different components and show how that changes the heat map. But I ran out of time. So what we did accomplish was a lot of the underlying functions and stuff for this thing. What we can do is, with very little work, we'd be able to add in more architectures. We'd be able to modify the code that this is running. We'd be able to see how all of this different stuff changes. Unfortunately, I'm going to be graduating, so I will not be continuing this work, and I was unable to finish this up because we had less members of our group than we were originally anticipating. But I did learn a massive amount both about linear algebra methods and numerical approximations, which are very relevant to me as I am a physics major, and also learned a lot more about the ways that these different components interact with each other, and kind of how this visualization was not just good for students who haven't taken computer architecture, but also good for me, and going into a lot more detail there. And these are the sources for my presentation. Thank you very much.